All right, so in the unit so far, we have talked about having functions like e to the x or sine x or cos x, or the rational function 1 over 1 minus x. And we've talked about how those functions can be represented using a polynomial. And we called polynomials either Taylor or Maclaurin, depending on where they were centered at. And so once you have those polynomials, I think the kind of realistic thing to do with them, or the reason that they have a purpose, is because you could find the polynomial to evaluate something if you were unable to use the function itself. Because, you know, those are all decimals we have to use our calculator for. So that's kind of the benefit of it. And I think the next question you want to ask yourself when you use a polynomial to approximate something is you want to know, well, how far off is my answer then if I use this polynomial to approximate it rather than using the function itself? So when we start talking about how far off the answer is, that's the error of the answer. And the error bound is just saying kind of a conservative estimate of like how far off we expect our answer to be. So the definition of an error bound is it gives the largest possible error. So when they say like, oh, I think that girl's 15, like give or take a year. The 1 year would be like the bound of how far off you think that your guess could possibly be. So when we talk about the estimate here, the estimate that I'm referring to is using a polynomial to approximate rather than evaluating specifically into the function itself. Okay, so using a polynomial to approximate a value rather than evaluating the function. All right, so there are two types of error bound that we're going to look at. One is the alternating series error bound. The other is Lagrange error bound. And alternating series is a little bit easier, so that's what we're going to start off with. Okay, so the true evaluation of a function would be the series, the entire series, the infinite series. It would be every single term of the series is exactly what you would get if you evaluated the function. But we're not going to spend our whole lives doing these problems. So that means that we're going to use partial sums of a series to evaluate the functions approximately. All right. So if a series is alternating and decreasing, which is basically just saying that the series is converging, the series converges, the error bound can be found by taking the absolute value of the next term. So if your last term was a sub n, then the error bound would be a sub n plus 1. So if your term is you're going up to the 5th term, then the 6th term is the one that would show you how far off your answer could possibly be with a conservative estimate. So here when it says the formula is that the error is less than or equal to the next term, what we mean when we say error is we're saying the actual value minus the approximate value. Or vice versa, you could switch those, put those in different places, and that's why we call it, we put it in absolute value because it doesn't matter if it's positive or negative, it's just the distance between those two numbers. So how far off you are is determined by subtracting the value that you guessed from the value that it truly was. And that's going to be less than or equal to the next term. So for example 1, it says to find the error bound using the first 5 terms to approximate the value. So when I look at this, I have to first say that it's an alternating series that is decreasing. So we can use the alternating series error bound. And you need to get in the habit of writing that. Anytime they don't tell you specifically that that's the error bound you're doing, then you need to specifically say that that's what you saw and that's why you were allowed to use that. So my first term, I would plug in 1. So negative 1 to the 2 divided by 1 would be 1 over 1. Negative 1 to the 3 over 3. Over 2, just kidding, I plugged in 2 to get that. And then 1/3, and then 1/4, and then 1/5. So they didn't tell us what number we were plugging in, but whatever we were trying to evaluate is approximately 0.783, which is that fraction. So it's approximately 47 over 60, which is the decimal 0.783. So that's our guess as to what we think the value could have been. That's our approximate value. So we're going to say if we wanted to know the bound of like how far off could our answer be, it's going to be the next term of the alternating series. So if I follow the pattern, the next term is going to be negative 1/6. So that means that our answer, the actual value, so I'm going to say the value of f of x, not approximate, but the actual value of f of x is going to be between minus 1/6. So it's going to be between 0.617 and 0.95. I think the value is probably 0.873. That's like my best guess. However, if I wanted to give it a boundary of what I think it's between, the bound is 1/6, and the interval that would mean that the answer has to be between is 0.617 and 0.95. So the real answer is somewhere in there. And depending on how the question is phrased, any piece of this could be the answer that you're supposed to give. So based on the question that was asked here, find the error bound, the answer for this particular question is 1/6. 1/6 is the error bound. Okay. Example 2 says, given the series, how many terms are required to get the error approximation to be less than 0.00005? So we're going to say the error has to be less than or equal to the n plus 1 term, which is less than or equal to, or just as less than, 0.00005. And since I'm doing this problem by hand and not using a calculator, I'm going to say 10th, 100th, 1000th, 10,000th, 100,000th. So that's 500 thousandths. Okay. Now this isn't an absolute value sign, so I'm not going to worry about the fact that there was a negative 1 there. Because it would be positive 1 when I put it in the absolute value. So if I want the n plus 1 term, I just have to plug in n plus 1. So I'm going to have 1 over n plus 1 to the 6th. Okay, so 5 goes into 120 times. Okay, so I've got 1 over n plus 1 to the 6th is less than 1 over 20,000. I will go ahead and multiply the 20,000 over here, multiply the n plus 1 to the 6th over there. So 20,000 is less than n plus 1 to the 6th. Oh, I forgot this is a calculator problem, because I don't know about you guys, but 6th rooting that is going to be rough. So if you 6th root 20,000, you get n plus 1. Actually, let me keep these on the correct side. Let me do that. 6th root of 20,000, 5.210. So 5.210 is less than n plus 1. Subtract the 1 over. So n has to be greater than 4.210. So, and we know that our terms have to be whole numbers. You can't have the 4.2 term. So since n has to be greater than that, we're going to say that n equals 5. So if you wanted your answer to be accurate to that, like more accurate than that approximation, then you would need 5 terms to make that accuracy happen. And the error bound then would be based on the 6th term. Okay, I was a little bit of a bad example here. I messed up the video the first time I made it, so I did this on the first video, which I then messed up. But I should have said before we even got started that this was an alternating series and it was decreasing, and so we used the alternating series error bound. My bad. Okay, So 5 terms is what we would need to get the approximate answer that we were looking for, and it was the 6th term that would have given us the level of approximation. The 6th term that would be the bound, actually, the error bound. Okay. Example 3 says let a sub n equal 1 over n ln n for n is greater than or equal to 3, and then they're telling us to look at this series. They want us to identify the properties of this series that guarantees that this series converges, and then explain why the sum of the series has to be less than 1/3. So when I look at this series, I'm going to go ahead and write out the series. So it was this times 1 over n. So that means that the series from n equals 3 to infinity is -1 to the n plus 1 over n ln n. And the properties that would guarantee that the series converges, we're just going to go ahead real quick and do the alternating series test. So the limit as n goes to infinity of 1 over n ln n is 0. And then we show that the terms are decreasing. So check, check. So that means that the series is converging. Okay. Next, they want us to explain why the sum of the series is less than 1/3. And to do that, we're going to use error bound. So I'm going to say this is an alternating series. It is decreasing. So we're going to use alternating series error bound. This is not like a special sentence that you have to memorize. You just you have to get the alternating series and decreasing in there, and then you have to say you're using the alternating series error bound. But however you want to phrase it is fine. All right, so what I'm going to say now is if we are going to explain why the sum of the series has to be less than 1/3, then I'm going to use the worst possible approximation to prove that. I'm not going to say, okay, I added up the first 50 terms and this is what I found. I'm going to say, okay, let's go ahead and use only the first term to do the approximation, and that will prove it for us, okay? So we're going to say the worst approximation is using only the first term. And so that means we're going to say that the sum of the series is 1 over 3 ln 3. That's the first term, okay? And I'm going to go ahead and write out that decimal real quick. 0.303. Okay, so if that is the case, that means that the error bound is less than or equal to the next term, which is -1 over 4 ln 4. Okay, and so that decimal right there is 0.180. Okay, so what we are saying then is that the actual value is somewhere between 0.303 plus 0.180 and 0.303 minus 0.180. Okay. Now, when you look at this, which is what I did, I was like, yeah, 1/3 is actually right in between those, so we didn't prove anything. However, when we are doing something like this and we are doing like our worst case scenario and using the first term, what you have to understand is that the first term is that 0.303, and the next thing that you're doing is you're subtracting a number that is smaller than that, and then you're going to add a number that's smaller than the number you subtracted. And then you're going to subtract a number that's smaller than that. So really, having an upper bound that's bigger than the first term does not make sense. You can't have an upper bound for this interval that is bigger than this decimal. So really, we go back here and we say, okay, The biggest possible number we can truly have is 0.303 because we understand how error bound works. That we are looking at a value that truly could have happened. And since this is the first term, this is our worst case scenario, the very first term is going to be the very highest that we could have possibly had, okay? This is something that you don't have to worry about in your interval when you're looking at like, oh, I did the first 5 terms or the first 3 terms or the first whatever. But if you're looking at a worst case scenario and you're only using the first term, then you would say that 1/3 ln 3 has to be this upper bound right here. Okay, so what we are saying is that the actual value, and I'm going to go ahead and write this using exact numbers, the actual value, I'm going to say AV for short, is between 1/3 ln 3 minus 1/4 ln 4, because that's what I actually did to get that decimal. So it's somewhere between 1/3 ln 3 minus 1/4 ln 4 and 1/3 ln 3, and 1/3 ln 3 is less than 1/3. And I know that it has to be less than 1/3 because its denominator is bigger than 3. So 3 ln 3 is bigger than 3. And so it has to be overall a decimal that's smaller than that decimal right there. And so this is how I prove it. So again, that line of reasoning I used is I found my next term. And then I said, okay, but if we're doing worst case scenario, we can't take the highest number and add something to it because you can't get past your highest number. And the highest number we had was 1/3 ln 3. All right, there is one example on the next page, but I think I'm going to go ahead and leave that for in class so that we can talk about that one together.